Hey everyone, this is another episode of Live Contract Reviews, and we actually running out of contracts to review. So I'm searching for some stuff that's still interesting. I still don't want to review lockup contract because it's kind of big and complicated and not as fun. So if you build in on NEAR and have your own contract that you want to review, let me know on any of the channels and we will consider reviewing it next time. So today we're going to review uh, something interesting. It's a basic fungible token contract, but it's written in pure Rust without NEAR binding, without NEAR SDK. It uses no STD and it tries to minimize the size of the contract as much as possible. So let me start presenting this. So this contract is, if you look in the core contracts, there is a PR that is called fast fund token. And if you build it, basically I can remove cargo log to demonstrate and like do cargo clean from this folder. If you build it, well, it takes 0.07 seconds to actually build it. And the size of this is about 1400 bytes. But it does implement somewhat like a fungible token that allows you to transfer tokens similar to Solidity style arguments, where at first, except without RLP encoding, but you'll see what's going on here. Okay, so to start, I want to show the cargo TOML file. So we basically have a standard set which does overflow checks and like optimizing for size with small s, but there's no dependencies at all. Like for this, we don't need dependencies. The target is still our lib, which is what we use for WebAssembly. And a contract starts by saying I'm a no STD contract, which means I don't import any standard library and allocator. I enable core heuristics feature, and there's just to solve some warning. I don't remember why I needed this. Now we need to define a panic handler. The panic handler is usually defined by STD. It's what throws this beautiful error about unwrapping. So let's say you did a panic or you made some operation in Rust that's supposed to throw an exception, a panic. Then STD handler kicks in and it unwraps this error and like drops a pass on it, and it actually prints like entire beautiful error. Instead, here we don't put any error if we panicked at core. So we just like say, okay, abort, and that's it. Like no, we don't touch the panic. This minimizes the amount of code we need to handle it. And this contract is mostly done to minimize the code. So there is a no mangle. That's something with WebAssembly where you don't rename methods or some other stuff that you do. It also minimizes the code. Now I have a bunch of constants that I use here. So I use a state key for supply, a total supply. Then I got the length and how many bytes it takes. Wait, no, this is for U256, how many U64s I need. And then just cast it to usize. Now I define a type U256, which is just an array of U64s. You'll see why I'm doing it this way. Now, I actually don't know if this contract works. I haven't properly tested it. And maybe there are some problems with the orders of how the integers are represented, but it can be solved. So now we import a bunch of stuff that we need. So this is what's usually abstracted by NEAR SDK Rust. And this is C style imports. So this is external host methods that will be available by provided from the VM. And WebAssembly has only like 2 or 4 types supported. It's a U64, I64. Actually, WebAssembly, I think, only has I64, but we cast I64 to U64. No, I don't remember. Anyway, so this is work with, yeah, go ahead.
I was just saying, in WebAssembly, that everything is, there is no signing until you actually like use an instruction, and then the instructions are signed. So, yeah.
Right. So yeah, there's like 2 types, but in like our VM at NEAR, we treat U64 as I64 in WebAssembly, whatever the base type. So there's a bunch of imports. This is to work with memory and how our VM mostly work. We have some internal memory within the VM and memory available to the contract. So example here is registers. So you can put something in a register, you can read from a register, and you can do certain operations on registers. You'll see how it works. Then there's a panic method that stops the execution, and this is unnamed panic. So it doesn't provide any string to panic or like any message, just saying the contract panicked. Now you can get a predecessor. So this is the account ID that called the contract directly, and it will put it into a register ID. So registers from 0 to U64 max minus 1, because the final one is used as like for some other purpose. Now input is when your method is called, your contract is initialized. It doesn't really put these arguments in JSON straight to your method. Instead, we put them into context that you can read using this input method that will put this data into a register. SHA-256, this is another method that computes the hash. You give a value by giving a pointer in the memory and a length, and then you put where to put the result. It will put it in the register. Value return, same way. When we return a value, we cannot just return a JSON from the method. Instead, we need to call value return and provide a pointer in the memory. And the reason is U64s everywhere. Like in order to return 2 values, for example, from your method, you need to return a pair, which WebAssembly does not support, I think. That's why if you want to return 2 values, you need to like instead use host method. Now storage write takes a key by length and pointer, a value by length and pointer, and a register ID. So length and pointer works interestingly. You basically can specify a length to be U64 max minus 1, and that will indicate that instead of memory pointer of your contract memory, you will use a register directly. So you will read the value from an existing register. This avoids copy, so you don't need to like extract the information from a register to your WebAssembly memory, and then from WebAssembly back to the register, or like to the host. And for large object, it actually saves you a ton of gas. So value lengths is similarly, and where to put the previous value. If the storage contained a value at this key in the past, then it will be written that into this register and will return the amount of bytes it read. I think maybe it returns whether it read it or not. I think it returns like 0, 1, which means there was some value, there was no value. Now, storage read, you get a key and where to write, and whether it wrote it or not, I don't exactly remember, but we'll see by the contract. Storage remove is to remove a value, and it returns you again a previous value. And storage has key is whether there was a key or not, the given key. Now I defined two functions that I'll use to add. So basically it implements a mass on top of my fake U256 objects. So it takes two values to sum, and it returns, it writes the value into result. And the way it works, it uses Rust's, so it assumes the first byte of the value is the lowest. It uses overflow and add, and it uses the implementation where we first add A to B bytes, corresponding bytes. Then if there was an overflow in the past, so it was carry to this essentially byte, that adds to this value, and if it overflows, which is, it cannot really, I think. Oh, yeah, it can, yes. And then it computes if it was overflow or not, and records the value. Then if we still have a carry at the end, then we panic because we overflowed EU256. Same way implemented sub. Except in reverse. So it subtracts from A to B. Then if there was like a carry, we also subtract it. And if it became under, then we move it to the next. So it's like a subtraction. Does two methods make sense so far? So what is overflow and sub returns? It returns the overflowed value and whether there was an overflow. So for example, if you subtract in U8, so in up to 256 values, so if you add 128 plus 128, it will return 0 and there was an overflow. If you add, for example, 128 plus 127, then there's no overflow, so it will return 255 and no overflow. Overflow and add. And if you, for example, add 128 plus 129, then it will return 1 and overflow. and it panics again if A is less than B. So this is initialization. The way you write methods, it's basically just a method. There's no return, there's no input. They all mark unsafe because we access external C APIs that we imported here, which are considered unsafe by Rust. We add no mangle, so the method name stays. And we do the following. So first we check, as traditionally, whether the contract was already initialized, and we do this by checking if the access or if the supply key is already set. So if storage case key equals 0, I don't know what means 0. Yeah, I cannot really go there. I assume basically it should be if there is already a key, then we should panic because the contract is already initialized. Now we read the input into register 0. Then we get the length of the input by calling register len. Oh, no. And we check that the length of the input is expected as we want. So, and the way we want it is first 32 bytes, which correspond to the first U256, is the account ID of the owner, or SHA-256 of the owner account ID. And the last, the second U256 is the total supply. Then we initialize the buffer for the given size to of U to U64s to read the value. So it doesn't matter whether I'm gonna use bytes here or U64s. It's still gonna be a consecutive piece of memory that I'll allocate in my heap. And I'm allocating 8 U64 values, which is 64 bytes. Then I'm reading a value from the register here, and I get this information now locally. And what I'm doing, I'm just setting a supply to a second second byte, a second U256. So pointer is measured in bytes, so that's why I need 32. And I'm saying, please write a register 0 now, because I don't need register 0 anymore. So, and then I write the owner's balance. Again, it's a key, the owner address of 32 bytes, and same value. So entire total supply is now owned by the owner. Now the next thing is transfer. So basically what this method did, it's initialized the total supply key, which now we can use if there's already to prevent a second initialization. And we also initialize the owner's balance. Now, in order to transfer, we need to do the following. So some predecessor account ID called us. We calculate their address, then we need to read their value. And we need to, so the first 32 bytes gonna be who should receive tokens, and the last should be the amount to transfer. So let's see how we do this again. So again, transfer doesn't actually return or takes any input directly. We read the input, we put it into a register. Well, not yet, but we put it into a register. We take the length of this register. We expect 64 bytes. And we allocate buffer and read it. So this one is like exactly the same as in before. So we can actually move it to a helper method. Now, we don't need to register 0 anymore because we have everything in memory. We read the account ID of the predecessor into register 0 again. So now we have the account ID, which is a string, in the register 0. What we do, we say, now go and hash this value. We pass a length of max, which saying that instead of reading from my wasm memory, you should read it from register 0. And it reads this value, and where to put it, back to register 0. So we override this value now. So instead of extracting this value and allocating a known size, which is hard to do without allocator, so we can only allocate a fixed size. So for example, in this case, we will have to allocate 64 bytes that are required for the account ID. What we did with these two operations, we actually hashed the value directly in using the host methods and put it back to register 0. We still don't read this hash yet because we don't really need to know who the owner is. It lives in a register and we can just use it. But what we need is to know what's the balance of the owner. So we read the value from using a key of register 0 into register 1. And if there was no key, then we should panic. Now, now we get the owner's balance in register 1, if it existed before, and we read it. So we allocate 4 bytes for this, and we read it from register 1. So now we don't need register 1. Now we get the transfer balance. And we allocate the new balance initialized to zeros as well. And we say subtract from the owner the transfer balance and put it into a buffer of new balance. So what happens here is we basically do overflowing subtraction. And if it overflows, which means the transfer is larger than owner's balance, then it will panic. Otherwise, it will put the new owner's balance into new balance. And we store it. We update the owner's balance first. So again, the key is in register 0. We say we're gonna write it into register 1. Oh, read it to register 1. It's like the old value, it doesn't matter. Now we need to update the receiver balance. For this, we allocate receiver's balance and we try to read it. If it exists, we actually read it. If it doesn't exist, then it used the balance is 0. So read the register 1 and put it back in the balance. Now we add using the so we add receiver balance to the transfer balance and the amount back to reusing the old buffer because we don't need it anymore. If it doesn't overflow, which it key not. Then we add it to storage write. So the key is the receiver ID, and the value is the new balance. And that's it. So this is a transfer. It basically does the following: just reads the balance from the owner, figures out who the owner by hashing the predecessor, then updates the owner's balance, and then increments the receiver's balance with the new transfer amount and put it back. If the receiver is the same as the owner, it's not a problem because we first subtract from the owner's balance and then add it back to the owner's balance. And now there's two view methods. So first method is get balance, and the way we do views, you will see. I guess there's no total supply, but we can add total supply as well. So get balance reads the input. It expects one element. Which is addressed to check the balance. We actually don't need to read it, I assume. Right. Yeah, I think we can rewrite it because we don't really need to read the value, because we can just use a register. So we can read straight from register 0 and put it in register 1. And otherwise, we need to return 0. If the account doesn't exist, then we need to return 0. So we can remove this too, and it should work as well. So let's say if you recompile this, so it got slightly less bytes because we decreased some code that we don't need. Anyway, so this is an interesting implementation, or like interesting idea how you can write contracts that don't use SDK, and they optimized for speed and for size. And the idea why you might want to use this type of stuff is, let's say you want to do some operation that requires a large input, and you don't want to copy this input out of the memory or like into host memory. I think we're still missing some items that you may need to. Let's say if your input actually requires you to do certain serialization and you need an offset, then we don't really have a way to like read the partially read the register, or apply certain operations on the register, like maybe some other stuff. Anyway, that's entire contract, and I would like to answer questions if there's any.
Can you, this is crazy good. Can't wait to watch the beginning part. So can you also read registers for the contract code? I'm curious, like, do you have access when you're reading registers? Can you access the state of like the contract code?
No, but I guess we can expose this stuff. There was also some optimizations on VM side, which potentially doesn't need to read the code if we have a compiled binary in memory already. So it may not even read it from the try, it just need to read the hash of the code. All right.
So the stuff like, you maybe already answered this, read register, register length, write register, those are like fundamental Rust things, or this is fundamental, like what is doing the actual call there?
So this is actually VM, like our WebAssembly VM methods. So we have the concept of registers. I think you can have up to 100 registers, something like this. And the total register size is limited as well. And then you have ability to operate on registers. On the like through basically what they allow. The problem is you cannot access memory from host. Like our host is near core node, and we are kind of guest contract or guest program that runs on a host in their VM. So they can access our memory because they allocated our memory, but we cannot access from inner to their memory. In order for my program to get any information from the host, they need to write it into my memory directly instead of returning me, because the only value they can return is like one value in U64. So that's why all the operations like read register is saying, I first allocated some pointer and amount of bytes that I need to read. And then I call my host to say, okay, I know where to put information now. Go put it into this pointer. And the size is known because register has already a length. So I can say, just go put me info here into this buffer.
Gotcha.
And
so is it true the registered length is 100, you said, max?
Number of registers. I think we allow you to have 100 active registers at the same time. I think you can drop them somehow, like you can drop a register. I don't remember if we have this API or not.
I see it's a U64. Curious.
No, I think, well, all of our input is U64. We don't have U32 at all. We just decided that all values going to be U64. Even the one that we may not need, we just decided that, like, whatever, to be future proof in case we like need more than 4 gigs of memory at some point.
This would be really fun to run against. You know, I don't know if you've seen it, but Josh made a graph of, actually you did see a graph of the different data structures adding the same data, and like it'd be really fun to make a graph to see the optimizations of this approach.
Right. So also we don't probably need overflow checks because I actually handle overflow manually. So let's see if when I change it to false, what's going to happen. Like, will it actually decrease my size of the contract? No, it doesn't. So it's still the same.
Would you?
And that's probably because, yeah.
Sorry. Would you guess that it's a gas and WASM file size improvement, or like one or the other?
Yeah, I actually don't know. So in theory, it should handle the overflow. Maybe because I do overflow, or like I do regular sum in two places. When I do pointer plus length, but maybe because it's static, like WebAssembly just pre-allocated this memory ahead of time, so it just give me exact position in value, because I don't really have a heap allocator. I think it's stack. So that's why this operation is also pre-computed on a compiler time, which means I don't do any sum anywhere in this entire code. And the only sum I do is here. I use overflow in sub and overflow in add, which are already handling overflow. So potentially that's why it doesn't affect the value. So let's actually try. Let's add +1 to see what's the difference. So yeah, this is with overflow. You can see by just adding +1 here, I increase the size by 300 bytes. And if I disable overflow, oops, I actually decreased it by 1 byte. Wow, magic. Yeah, so one optimization I can do is I can try to write a method, read input, and put it here, and then return buff. Right, how I should do it like this. Okay, let's see if it compiles. It does. So I'm back to the original size. Now, if I replace this part, oops, no, this part, yeah, I got like small improvement in like by removing replicated code. Anyway, I'm not sure storage has key should return 0, 1. I suspect it's an issue, and maybe I should actually return 1 here, or like check for 1. And to check this, we can look at the Nomicon. Let me show a different window. Cool. So if you go to binding specifications, there's a bunch of stuff. What we're looking for is storage. I guess it's try API. So we need storage has key, and if the key is used and 0 otherwise, so we need to say if key is used, then it's 1, otherwise it's 0. Okay. So if you ever want to write low-level API, this is a good place to read. Or just go straight to NEAR core and read it from the code. Okay. Cool.
There should be in the documentation. And you can just hover over it.
Well, the reason why documentation is not there is because it doesn't actually link anywhere. So there's a 0 dependency on my contract.
Oh yeah, I forgot about that. Yeah. Yeah, there should be a way to like just link with the API and nothing else, and then that way, like, you don't have to copy and paste that part.
Yep. Yep. And this actually would be cool to.
Better version that I had the similar one for assembly script, and I did a build presentation with Matt on comparing the WebAssembly to EVM, and I think this is a much more interesting example. Mine was just a simple counter.
Mm-hmm. It would be interesting to actually write a simulation test for this, but I'm not quite sure how to. Like, we cannot really use this.
You could make like a fake
level
interface for it, and then just encode the inputs that way. Otherwise, yeah, you'd have to like handcraft the like transactions, which isn't so bad.
No. Any other questions?
This is awesome.
Okay, cool.
Thanks.
Yeah, thanks for watching. I would again repeat, if you have contracts to review, let me know anywhere. You can find me on NEAR, and we will consider it for the next time. Thanks.